Set builder notation, introduction. So let's begin our discussion on set builder notation. As you know, we've been exploring different ways to define sets, listing out elements, describing them in words. But what if a set is very large or even infinite? Listing every single element becomes, well, impossible. This slide introduces a much more efficient method, set builder notation. The first point here states that it's a powerful way to define a set by specifying the properties its elements must satisfy. Think of it like giving a set of rules, rather than a list of members. The next line highlights why this is so useful. Instead of listing all the elements, which, as I mentioned, can be impractical or impossible for infinite sets, we describe the rule or condition that determines membership in the set. For example, instead of writing out all even numbers, we can simply state the rule: the set of all numbers that are divisible by 2. Finally, this notation provides a concise and elegant way to represent sets, especially those defined by specific characteristics. It's a bit like writing a mathematical sentence that perfectly captures the essence of the set. In the following slides, we'll break down exactly how this notation works, looking at its structure and working through several examples. We'll start with the basic format and then build up to more complex definitions. So, keep this introductory idea in mind. We're moving from listing to describing when it comes to defining sets. So let's begin our discussion on set builder notation. Set builder notation, understanding the structure. So on the previous slide, we introduced the idea of set builder notation, a way to define sets by describing their elements rather than listing them all out. Now, on this slide, we're going to break down exactly how this notation is structured. First, those curly braces, opening curly brace and closing curly brace, these are absolutely essential. They tell us without a doubt that we are defining a set. Think of them as the start and end markers for our set definition. Next, we have X. This represents a general element of the set. It's a placeholder. Imagine X standing in for any possible member of the set. It could be a number, a letter, even another set, anything. We use X simply because it's a common convention, but you could technically use any variable. Now, this is where it gets a little trickier. We have a vertical bar, vertical bar. This symbol is read as such that, or sometimes as where. It's the crucial link between the element, X, and the condition it must meet to be in the set. Finally, we have P of X. This represents the property or condition that X must satisfy. P just stands for property. So, P of X is a statement about X. This statement will either be true or false for any given value of X. If it's true, then X is a member of the set. If it's false, X is not. Putting it all together, the entire expression, set builder notation, is read as the set of all X such that P of X is true. So, we're defining a set by specifying all the X values that make our property, P, true. We'll see this in action with some examples on the next few slides, but understanding this basic structure is key to both reading and writing set builder notation. Remember, it's all about defining a set by its characteristics, not by listing every single member. Set builder notation, step-by-step examples. Let's move on to our first example of set builder notation in action. As we discussed on the previous slides, this notation is a really efficient way to define sets, especially when listing out all the elements would be tedious or even impossible, like with infinite sets. So here we have example 1, the set of even numbers between 0 and 10. We want to define this set using set builder notation, and we're going to call the set A. You'll see it written as A equals an opening curly brace X, a vertical bar, X is an even number and 0 is less than X, which is less than 10, and then a closing curly brace. Let's break that down piece by piece. The A equals opening and closing curly braces, that's just how we start defining a set. It signals to anyone reading it that we're about to describe the elements within that set. We're naming the set A. Next, we have X. Remember from the previous slide, X represents a general element of the set. Think of it as a placeholder. It could be any number, but it has to meet certain conditions to actually be in the set. Then comes the vertical bar symbol. We read this as such that or where. It's the key that separates the element, x, from the conditions it must satisfy. After the such that, we have x is an even number. This is the first property our element x needs to have to be included in set A. It's a condition that x must fulfill. And then we have 0 is less than x, which is less than 10. This is our second property. It tells us that x must be strictly greater than 0 and strictly less than 10. So, it has to be between 0 and 10, not including 0 or 10 themselves. Putting it all together, this set builder notation reads as: the set A contains all x such that x is an even number and x is between 0 and 10. If we were to list out all the elements that satisfy both of those conditions, we'd get 2, 4, 6, and 8. So, A equals the set containing 2, 4, 6, and 8. Notice how much more concise the set builder notation is than actually writing out all the elements, especially if we were dealing with a much larger or even infinite set. We'll see more examples of this as we go through the next slides, building up your understanding of how to construct these set definitions. Set builder notation, step-by-step examples, continued. Let's move on to our second example of set builder notation. As you remember from the previous slides, we're learning how to define sets not by listing out all the elements, which isn't always practical, but by describing the properties those elements must have. So, this example asks us to define the set of all positive multiples of 3 that are less than 20. Here is how we write that using set builder notation. We have b equals open curly brace, x such that, close curly brace. Remember, the b equals open curly brace part simply means we are defining a set, and we're naming it b. Now, x represents a general element of the set. Think of it as a placeholder. It stands for any number that might be in our set. Then we have the vertical bar symbol, that's read as such that. It's the key that separates the element, x, from the condition it needs to meet to be included in the set. After the such that, we have x equals 3n. This is where we define the property. What this means is that x is equal to 3 times another number, n. Since we're looking for multiples of 3, this makes perfect sense. And importantly, n is specified as being a positive integer. That means n can be 1, 2, 3, and so on, any whole number greater than 0. So if n is 1, x is 3. If n is 2, x is 6, and so on. But we're not done yet. We also have another condition. X is less than 20. This restricts the multiples of 3 to only those that are smaller than 20. We can't include 21, 24, or any larger multiples. Putting it all together, this set builder notation tells us that set B contains all numbers that can be written as 3 times a positive whole number, and are less than 20. If we were to list out all the elements that satisfy these conditions, we'd get 3, 6, 9, 12, 15, and 18. So B equals the set containing those numbers. In the next example, we'll see how to incorporate even more complex conditions, and also how to use standard mathematical symbols within our set builder notation. Set builder notation, step-by-step examples, continued. Let's move on to our third example of set builder notation. As we've practiced, this is all about defining a set by describing the properties its elements must have, rather than listing them all out. This is especially useful when dealing with potentially infinite sets, as we'll see here. So, example 3, the set of all real numbers greater than or equal to -5. We're going to represent this set as C, and here's the set builder notation. C equals open curly brace, x vertical bar, x is an element of the set of real numbers, and x is greater than or equal to -5, close curly brace. Let's break that down piece by piece, just like we did with the previous examples. First, C equals open curly brace, dots, close curly brace. This simply tells us we are defining a set and giving it the name C. The dots inside the curly braces indicate that we'll be specifying the elements based on a condition. Next, we have x. Remember, x is our placeholder. It represents any number we're considering as a potential member of this set. Then comes the vertical bar, which we read as such that it's the key that separates the element, x, from the condition it must meet. Now this is where it gets slightly different. We have x is an element of the set of real numbers. In mathematical notation, this is written as x belongs to the capital R. The capital R, written as R, represents the set of all real numbers. That includes all rational and irrational numbers, positive and negative, fractions, decimals, everything on the number line. So this part of the definition is telling us that x must be a real number. It can't be an imaginary number or anything else. Finally, we have x is greater than or equal to -5. This is the lower bound for our set. It means that x must be -5 or any number larger than -5. Putting it all together, this set C contains all real numbers starting from -5 and extending infinitely in the positive direction. So it includes -4.9, 0, 3.14, 100, and so on, all the way to infinity. This is a great example of how set builder notation allows us to concisely define an infinite set. Now, on the next slide, we'll recap the key takeaways from all these examples and also discuss some common mistakes to avoid when working with set builder notation. So, make sure you've understood this example before we move on. Set builder notation, key takeaways. Let's recap everything we've learned about set builder notation with this final example slide. So, as we've discussed, set builder notation provides a concise, meaning short and to the point, way to define sets based on the properties their elements have. Remember, instead of listing everything out, we're describing what makes something a member of the set. Now let's revisit the general form. We have a set defined as x bar vertical bar p of x, where the x represents a general element of the set. The vertical bar is read as such that, and p of x represents the property that x must satisfy to be included in the set. Think of it like a rule. If x follows the rule, it's in the set. Understanding each of these components, the curly braces, the element x, the such that symbol, and the property p of x, is absolutely crucial. It's not enough to just see the notation. You need to know what each part means so you can both understand sets defined by others and create your own definitions. We've practiced this with our examples, building up from simple even numbers to multiples of 3 and finally to real numbers. And finally, remember that set builder notation really shines when dealing with infinite sets or sets that have really complex rules for membership. Trying to list out all the elements of an infinite set would be impossible, but describing the rule using set builder notation is perfectly manageable. It's a powerful tool that will be incredibly useful as we move forward in our mathematical studies. Now, on the next slide, we'll quickly go over some common mistakes to avoid, so you can be confident in your use of this notation. Set builder notation, common mistakes. Remember, in the notation, we have a general element, we've been calling it x, and then a property that x must satisfy. It's crucial to keep these distinct. X is just a placeholder for any potential member of the set, while the property, which we've denoted as p of x, defines the rule that determines if that x actually belongs in the set. Don't mix up what you're testing with the criteria you're using to test it. We've been using a vertical bar. It looks a bit like a pipe, and reading it as such that or where. This symbol is absolutely vital. It's the bridge that connects the element x to the property p of x. Without it, the notation simply doesn't make sense. It's telling us we're considering elements x given that they satisfy this condition. So always make sure that vertical bar is there, clearly separating the element from its defining property. Sometimes we need to be clear about what kind of numbers we're dealing with. For example, if we're talking about real numbers, we explicitly write x belongs to the set of real numbers. The symbol for the set of real numbers is a capital R with a double bar through it. So, we'd write that as x belongs to R. If we don't specify the domain, it can lead to ambiguity or incorrect interpretations. It's good practice to always state the domain, especially when dealing with more complex sets. When defining the property, p of x, strive for simplicity and conciseness. A complex, convoluted property is harder to understand and more prone to errors. Try to express the condition in the most straightforward way possible. If you find yourself writing a very long and complicated property, take a step back and see if you can break it down into simpler parts or rephrase it more clearly. So we've covered how to use set builder notation, and now let's quickly go over some common pitfalls students often encounter. This will help solidify your understanding and prevent mistakes when you're working with these sets. By keeping these common mistakes in mind, you'll be well on your way to mastering set builder notation and confidently defining all sorts of sets, even those that are infinitely large or defined by intricate rules.